Now the work done by a force of constant moment or by a constant moment. Suppose that we have this rod which is affected by a force which is all the time perpendicular to the rod, and the rod rotates through an angular displacement delta theta. Then we say that the work done by this moment is exactly the moment times this delta theta. Application 3. Ali opened a door of width r equals to 70 centimeters, and this width represents the distance away from the axis, by a force of magnitude F equals to 1 Newton and always perpendicular to the plane of the door. Calculate the moment done by the force to open the door by delta theta equals to 30 degrees. What should we do here? In order to solve such exercise, and we said before that the work done by a constant moment is just the moment times delta theta. Then first let's find the moment. This moment is exactly F times OA times sine 90 because it's perpendicular to the plane of the door. F is 1, OA is 0.7, or R is 0.7. It's 0.7 Newton meter. Delta theta should be in radians, then it's pi over 6. Pi is 3.14 over 6, it's 0.52. The work then is given as moment times delta theta, 0.7, and the last answer is given as 0.366 joules. What is meant by power? Power is the time rate of energy transfer, but work is a method of energy transfer, so the power can be defined as the time rate of doing work. Starting with average power, it is the amount of energy transferred or the work done divided by variation of time delta t. Here we can say that the P average equals to delta E over delta T, or simply delta work over delta T. But also we have average power can be written as V average. How? If we apply delta work over delta T, but delta work can be written as F dot delta R, since we are dealing with constant forces, then we are talking about delta R. Delta R over delta T is V average, and here it is simply P average F dot V average. But since sometimes we talk about instantaneous velocity, then we talk about also instantaneous power, and it's F dot V instantaneous, simply it's just V. The SI unit here is watt, which is joule per second. Also in rotation, we can say that the instantaneous mechanical power in rotation is given as simply the moment times theta prime, the derivative of theta. And here comes the end of the third part, the work done by the constant moment and power. Please watch this nice video, and at the end, my dear students, after studying and watching this part, please solve extra sheet 1, and later you will be asked to do quiz 1. Goodbye.
In physics, the concepts of work and power help us understand and explain lots of things in our universe. Let's start with work. Positive work is the energy we put into a system, and negative work is energy that's transferred out. Think of positive work as money being added to your bank account, and negative work as money taken out. In the metric system, work and energy are measured in joules. As an example, let's take a beautiful old mechanical grandfather clock. We transfer energy into the clock when we turn the crank to raise the heavy metal cylinders inside the clock. When we do this, we're doing positive work, adding energy to the clock. And that energy is stored as gravitational potential energy. We can calculate the amount of work done by multiplying the force we apply times the distance over which we apply the force. To raise the metal cylinders, we need to apply a force equal to their weight. That is, equal to the force of gravity pulling downward on the cylinders. These cylinders weigh 300 newtons, which is pretty heavy, about as much as a small child. And if we lift them 1/2 meter, then we do 300 newtons times 1/2 meter, or 150 joules of work. Power is the rate at which energy is transferred. When we say rate, we mean the amount of energy transferred per unit of time. In the metric system, power is measured in joules per second, or watts. The term watt goes back to James Watt, who came up with the concept of horsepower to measure the amount of power produced by a typical workhorse. James Watt was a producer of industrial steam engines, and he wanted his potential customers to be able to make comparisons between his steam engines and a familiar quantity, the power they could get from a working horse. This was such a useful idea that the metric system unit for power, the watt, is named after James Watt. Following in James Watt's footsteps, let's compare the amount of power it takes to run this grandfather clock to the power we'd need to run a bright 100-watt light bulb. We can measure the power a person uses to wind the clock by dividing the amount of work they did by the time it took them to do it. If it takes 1 minute or 60 seconds to lift the weights, then they are doing 150 joules divided by 60 seconds, or 2.5 joules per second of work. They're adding energy to the clock at a rate of 2.5 watts. You'd need about 40 times as much to run a bright 100-watt light bulb. Before we let the clock run, the energy is stored as gravitational potential energy of the cylinders. It's like your bank account when you have just deposited money. But if we let the clock run, the cylinders slowly move downward. Energy is leaving the clock. In fact, when the cylinders get to the bottom, all the energy that we put in will have left. So how much power does the clock use? That is, how many joules of energy per second leave the clock if it takes 5 days for the cylinders to return to their original position? We can figure this out because we already know how much work we did when we lifted the cylinders, 150 joules. But this time it took 5 days rather than a minute. 5 days is 5 times 24 times 60 times 60 again, or 432,000 seconds. So we divide the work done by the time and find the answer of about 0.00035 joules per second, or about 0.35 milliwatts. That's a tiny amount of power. This clock uses so little power that you could run almost 300,000 clocks using the same power it takes to run one 100-watt bulb. That's right, you could run a clock in every house in a medium-sized city with that much power. That's a pretty amazing conclusion, and it took knowledge of work and power to figure it out.